we do? It's 3. Shall we start, or shall I wait for more guests to join? I would like to ask Masahito. Can I start?
Okay, please start.
Okay, so it is a pleasure to chair the final session of this workshop. The next speaker will be Professor Shintaro Yanagida from the Graduate School of Mathematics of Nagoya University. And his talk will be a probability distribution expressed by a Raka hypergeometric orthogonal polynomial. Please.
Well, thank you for the introduction. And I'm Shintaro Yanagida at the Math Department of Nagoya University. So, and as one of the organizers, I would like to thank all the participants and all the speakers for the contribution to this workshop. I think it is in great success. And I will put, I just put this slide in the chat box. So if we want to recall previous pages, then please see the downloaded file. So let me start my talk. This is based on collaboration with Hayashi Sensei, the main organizer of this workshop, and Hora Sensei at Hokkaido. He's about this workshop. And our paper is a little bit long one, it's over 70 pages, and it has various aspects. And today, due to the limited time, I can only explain mathematical part, or in some sense, technical part. So here is a plan of the talk. So before the middle break, I will first explain the conclusion and the setting. And as in the title of my talk implies, so the main object of my talk is certain probability distribution, which is expressed by certain hypergeometric series. So let me start with a recollection of what is hypergeometric series. The definition is given by this formula. So here, for example, small r. Small r means some. Small r denotes some non-negative integers. Negative integer. So 0, 1, or 2, whatever. And AIs denote denominator parameters, and small b's denote, sorry, A denote numerator parameters, and B denotes denominator parameters. And in any sense, this formula is defined as a series, formal series with variable z. And in the coefficient, we have the so-called rising factorial. So the definition is worse. So for example, in the denominator, we have 1i. So 1i means you can find that 1i is nothing but the I factorial in the usual sense. So anyway, we have such a formal series. And for the recollection, let me write down 2, 1. And let me switch parameters to A, B, and C. Then this one is nothing. The definition says that the coefficient looks like something like this. Okay. Something like this. And so this one is the classical Gauss hypergeometric function. And one more recollection is that if we have negative parameter in numerator, then this summation is a finite sum. I call 0 to n. The sum coefficient is Ci. And in my talk, this terminating series will appear. So the recollection is over. And here is the main result. And I will only explain this result. So let n and m and k be some integers, non-negative, and satisfying some conditions. And consider this function with variable x, given by some hypergeometric series for f3, and with some factors consisting of binomial coefficients. Then this function gives a discrete probability distribution for the variable x ranges from 0, 1 to n. So this is our main statement. And the statement will be clear for all of you, but let me recall what is the discrete probability distribution. So the theorem says that this function px is non-negative for this value, for this x. And the total sum is 1. Very clear. But these two statements is in fact very non-trivial. I want to stress this point. This one is very non-trivial. So let us recall the definition of this hypergeometric series. Then you can find that this 4f3 term can be expressed in this form. As I mentioned, the summation is finite. And rewriting this writing the coefficients, you can find that this summation is alternating summation. So here is some combination of binomial coefficients. So this part is non-negative. And the theorem says that this alternation sum is non-negative for this value. And it is in fact very difficult to prove this inequality directly from this defining formula of the function px. So this is the first item. The second item, the total sum is 1. This is a little bit easier one, because a little bit easier. And in fact, we can extend this identity to this theorem too. So instead of considering total sum, let me consider the so-called cumulative distribution function. What is cumulative distribution function? CDF. Right. So let me write again this function as px. Then this cumulative distribution function is nothing but the summation apart. So CDF is nothing but a partial sum of PU up to the given number x. And our statement, our second statement is that this partial sum is also expressed by hypergeometric series for F3. And yeah, there are some parameters, and these parameters are almost the same with the previous one, except one phase. So yeah, somehow the parameter is shaped. So anyway, the probability distribution function, PDF, is expressed by 4F3, and CDF is also expressed by 4F3. So this is our main statement. So the meaning should be clear for all of you. And but let me stress again that our statement. So again, so our distribution has a property that both PDF and CDF are expressed by OX3 series. And here is some comparison table with the known distributions. And let me here only mention this one, the so-called hypergeometric distribution. In this one, the CDF is expressed by 3F2 hypergeometric series, but PDF is not a hypergeometric series. So compared to this one, so our distribution has a property that not only CDF, but also PDF is also expressed by hypergeometric series. And so anyway, we have some complicated formula of distribution, but it is very difficult to understand what this distribution looks like. So here is some example of plots of our distribution. In the above figure, I plot the PDF itself with these parameters. So N is common and somehow NK are changed. So anyway, some unimodal distribution appears. And in the bottom figure, I plotted the CDF and partial sum. And here, so I fixed the ratios of MKL with respect to N. I fixed these ratios and I moved N. I increased N from left to right. So you can see that as the CDF graph converges to this Heaviside step function. And so we can expect at this moment that our distribution has some good property of asymptotic behavior, but I will mention in the last part of my talk for this asymptotic behavior of distribution. So anyway, so this is the end of the statement of the conclusion. And let me explain in the rest time of the first part, the setting or how we found the distribution given by some hypergeometric series. So we consider the so-called classical sure-word duality for SU2 and SN. So SU2 denotes the special unitary group of L2. Special unitary group SU2. And SN denotes the symmetric group. So SU2, and this is a group, has a natural vector representation of dimension 2. And extending this representation by diagonal action, we have the n-fold tensor representation on this tensor space C2 times n. And I will denote this SU2 action by left action. On the other hand, permuting tensor factors on this tensor space, we have a natural action symmetric group Sn. And I will denote this Sn action by right action. And you can check that these two actions, SU2 and Sn, commute. And I will depict in this situation like this. And what is sure-word duality? Sure-word duality says that this tensor product now a bimotion, so it has SU2 action and Sn action simultaneously. But so this space is decomposed into the reducible representations of this form. So this is a statement of sure-word duality. And here I denoted by U the SU2 irreducible representations. I denote it by rep. So this one denotes irreducible. Sorry for that. reducible representation. So U denotes SU2 reducible representation, and so subscript denotes the dimension of this representation. In the right factor, we have Sn reducible representation. And the classical representation theory of this symmetric group says that such an irreducible representation of symmetric group corresponds to a partition of n. And in our situation, only a partition of n of length less than y equal to 2 appears under the compositions given by this expression. And I should explain this symbol. This symbol, box times, denotes the tensor over C as three-linear space. So as a vector space, we have just one tensor product of U and P. And as a module, as a representation, so this symbol means that on the left hand, the left factor expresses how SU2 acts on this tensor space. The right hand two factors says that denotes how Sn acts on this tensor space. So this is a definition. This is a statement of Schauer duality, but I think many of you may not find out what this formula means. So let me explain in some example, and in the case n equal 1, 2, 3, at how this decomposition looks like. And in order to write down such a decomposition, I need some basis of this tensor space. So let me choose basis C2 to be 0 ket and 1 ket. For mathematician, this can be replaced by 2 vector. And instead of writing SU2, I denoted here SL2 and its standard basis. N equal 1 case. N equal 1 case is trivial, but let me check this decomposition. The variable x runs from 0 to 0. So I didn't explain this symbol. So this is just a Gaussian form. As the integer not superior to n over 2. So anyway, so in n equal 1 case, x ranges from 0 to 0. So we have just one component. On the right hand side, U2. So this is a SU2 representation of dimension 2. On the right hand side, so this is a certain black box, but in this case, 1, 0 case, this is nothing but a trivial representation of S1. So in any way, so in total, as a linear space, we have two-dimensional space. So we have the two-dimensional space, and this is nothing but the original description of this space. N equal 2 case, in this case, we have the variable x ranges from 0 to 1. So we have two components. This component O plus this component, direct sum. And the first component U3 denotes the three-dimensional representation of SU2, and V20 denotes trivial one-dimensional expression representation of S2. U in the second component, U1 denotes some one-dimensional representation of SU2, and V11 denotes the this is a sign representation of S2. So anyway, so this has 1 dimension and this has 3 dimensions, and I denoted here some explicit bases. So this 3 vectors give basis of this space. And this one dimensional is spanned by this vector. And in case 3 case, so we have still 2 components, x is 0 or 1. And in the first component, we have 4-dimensional SU2 representations. And this one denotes also the trivial representation of S3. U2 denotes SU2 2-dimensional representation. And this one denotes the so-called standard representation of S3. Anyway, this is 2-dimensional. And in total, we have 4-dimensional space, and this one also gives 4-dimensional space. And here I denoted some explicit basis for each component. So in many ways, we have 8 vectors on the right-hand side. And this is the 8 is nothing but the dimension of the original tensor space. So 3. And so we have anyway some decomposition. And then we have the projectors to each component for each x, 0 to 2, and what to. Then any normalized element of our tensor space gives a discrete probability by this formula. So here I should explain the meaning or physical meaning. And the physical meaning will be clear from this symbol. So curly H denotes our Hilbert space of quantum system. And Px gives the family Px, the family constant, the family Px. So X range is from 0 to something. So this corresponds to some measurement. Of X. What is X in physical meaning, in physical terms? This is nothing but J, the spin. This is nothing but the total angular momentum for spin. So physical meaning will be clear from these symbols. But so anyway, this is nothing but the background of in terms of quantum information theory. But I will not go to detail of such physics. Let me continue to my setting. So to get some probability, we choose some normalized vector. And our particular choice of this normalized element is given by this vector. So this is a tensor product of asymmetric state and symmetric state. In the second component, I wrote some complicated formulas, but this is nothing but the summation over permuted terms of this vectors. 1n minus n, 0 n minus n. Meaning is absolute. This is nothing but this is nothing but the tensor product of ones and zeros. So anyway, we consider this normalized vectors. And the time is running out, but here is the end of in the first half. So this here is just a recollection of our main statement. So we have some family of projectors from our tensor space to each reducible components, and we choose this particular very distinguished normalized element. Then this element Xi, or state Xi, gives some discrete probability identity by P. And this distribution function is given by this hypergeometric series. This is an answer. And so here is, I finished the first half of my talk. So I should break here.
So if there are any questions, now it's a good time to ask.
I think the meaning of statement will be clear for all of you. No difficult things happens in my talk.
Can I ask the one very naive question?
Hi.
Yeah, since the C2 is involved, I wonder there might be some relation to the quantum walk. So if there is such, very naive or could be stupid.
I don't have any idea.
So
actually,
you don't have motivation there.
No motivation, no direct relation.
I see.
As far as I understand. And actually, we, as Haya Sensei and Hora Sensei, and including me, wondered if there is some connection of probability distribution to other structures like quantum walks or like that. But we could never find related distributions in any sense. Distribution is somehow very isolated.
If let n goes to the infinity, or we make in some sense continuous limit, do we get the well-known function?
Yes, I will explain.
Okay, I should wait.
Yes. So I should explain that. So this discrete probability distribution is somehow, in some sense, isolated, but how to say, in the limit, in some asymptotic limit, so it has we can find various properties of such continuous distribution. I will explain only one aspect of that continuous limit later.
Yeah, in next part, maybe.
Yes.
Okay, all right. Thank you very much.
Any other questions?
Okay, so I have one comment. So maybe somehow quite difficult to understand the background of this one. This result has another background. So, Francesco, could you find some relationship with resource symmetry, resource theory for symmetry? This result somehow related to the, indeed, this result related to the resource theory for symmetry with respect to the permutation group. Can you find that kind of relation?
Can I find it from
So please back previous. So I want to show that relationship because initially this one has a symmetric. So this one has a maximal. This one does not change. But however, this one is not symmetric with respect to the permutation. So we want to consider how about asymmetry with respect to the whole permutation of this tensor product? this is one of our motivation.
Yes.
To see this kind of amount of the asymmetry. So back to previous one, that measurement is very important. This X correspond to the some symmetric space. X corresponds to the symmetry asymmetry with respect to the with respect to the permutation group. So then using this result, we can recover how much asymmetry this state has with respect to the permutation. So this is another motivation.
Yes. Thank you for your comment.
Can we proceed perhaps with the second part of the talk? If there are no more comments or questions, I will check the chat. The chat seems free from questions. All right, so I would like to proceed to the second half of the talk. Please, Professor Yanagida.
Thank you. So I will restart. And in the second, in the second half, so I will explain two items. In the first half, I will explain the outline of the proof of main theory. And in the second, I will answer to Moriyoshi sensei's to comment or questions. So in the first, so let me explain the outline of the proof of our main theorem. So the main theorem is a recollection of the statement. So anyway, we want to calculate this quantity. And this quantity, a projector and Xi vector. The Xi vector is given explicitly. So in order to compute this quantity, then we need some formula, some explicit formula of this projector. And such a formula of projector is given by the representation theory of Sn, very classical representation theory. And this strategy is due to Hora sensei. Let me explain his strategy or idea. So he is expressed the formula of the projector. So Px. So in our situation, Px is given by this formula. And here phi denotes the action of Sn. Phi denotes the right action in the expressions. And here is some numerical term, so some dimension of something. But such a thing can be computed by some well-known combinatorial formula. So this part is known. And here I denoted by chi the character of irreducible representation of the corresponding function. So anyway, in order to compute this one, we need to compute this type of summation. So we need to control or evaluate the value of irreducible characters. And in our situation, the so-called zonal spectral function helps us. So in our situation, so we are considering Sn, and here is a point. So we consider as the subgroup of this type. So M is the parameter n and k n. And so Sn and Sn cross Sn minus n. And this is a product subgroup. This pair is a so-called Gelfand pair, satisfying some conditions. And given such as Gelfand pair, we can consider the so-called zonal spectral function. And this is a function over the original group Sn. And the value is given by something like this. So anyway, here we find that the summation of values of irreducible characters. So it looks somehow similar to what we want to compute. And in our situation of for this particular elephant pair, we can, there is no formula of this value of zonal spherical functions. And this is due to the result. And the result is as follows. So this is a value of the zonal spherical function. And here we encounter another hypergeometric series. So this is a point for why our distribution is connected to hypergeometric series. So anyway, it is known by the result that the zonal spherical function of our elephant pair is given by 3f2 hypergeometric series. And this 3f2 function is a very special 3f2, and it is known as Hahn polynomial. And using this formula and some enumeration of K orbits, K denotes the product subgroup. The enumerating K orbits arising from our particular choice of Xi vector. Hora sensei discovered the following formula. So our distribution can be expressed by a summation of Hahn polynomial or 3f2 function. So this is Hora sensei's formula. Personally, I call it. So anyway, so here I did by Hahn summation formula. So this is nothing but summation. Anyway, so we have one explicit formula. But this this identity or this statement is already not trivial, but it is a little bit difficult to handle because this is a summation of 3f2, but 3f2 was a summation. So this expression is a double sum. So it is difficult to use for further analysis. So I wondered if there is some more simple formula. And here is the function. So this double sum, the summation of S3f2 can be rewritten as another hypergeometric series. So in other words, this double sum can be expressed by single sum. So this type of formula is called the so-called hypergeometric summation formula. As the meaning is that the summation of hypergeometric series is expressed by single hypergeometric series. And such a type of formula is variously known, but this particular identity cannot be found in literature as far as we know. So, but anyway, we can rewrite this double sum as a single sum. And then the resulting 4f3 series, 4f3 function is also a very special one. And this is nothing but the so-called Laka polynomial. And substituting this identity to here, we get the final statement of the main set. So now so this is the outline of the main set proof. And now the title of my talk will be clear, almost clear. So we have found some probability distribution that will represent it expressed by Laka hypergeometric polynomial. But here is another word, orthogonal. What is it? Let me explain. So here is some short recollection or short introduction to the Laka polynomial. Laka polynomial in general is defined as a polynomial of variable z in terms of 4s. So z appears here and here, and x appears here, and it is called the degree of this polynomial. And there are some parameters here, ABCD. And our distribution is given by some specialization of this Raka polynomial. This is the statement of our method. And for the orthogonality means the following. In the family of this Raka polynomial, moving up, running this degree variable x 0 to n, then this family is orthogonal with respect to some discrete weight function. So the orthogonality means this type of identity. So for different degree, just so the left-hand side gives some inner product on the function space with weight function degree. Then for different degree polynomial it is also in the same degree. So we have the normalized to 1. So this is the meaning of orthogonality. And Raka polynomial is a very special orthogonal polynomial, in the meaning that there is some classification theorem of hypergeometric orthogonal polynomials collected in the so-called ASCII scheme, so identity here. And there are some well-known orthogonal polynomial families, so-called SUSTech-Nagoya lower level. These are lower level families. Raka sits in the most top line, or more complicated. The most complicated family is classification scheme. And here, here various arrows appear. Each arrow expresses that specializing parameters of the source family. Then we can get the target family. So for example, Hahn polynomials can be obtained by specializing or taking limit of parameters ABCD in some way. So anyway, using Raka polynomial, so the Raka orthogonal polynomial, we get some formula of probability distribution. So let me explain the remaining time the asymptotic behavior of P. Or let me explain. So anyway, we have some very complicated distribution function. But is this complicated formula is useful in any sense? And here is one application of this complicated formula. The application is to some asymptotic analysis of distribution. But in order to explain that, I will mention another property of this Raka polynomial. So Raka polynomial is an orthogonal polynomial. So it satisfies the 3-term recursive formula of this form. So some linear relation between adjacent degree polynomials, x plus 1 degree, degree x plus 1 degree x, degree x minus 1. So these are in some linear. These satisfy some linear equation. But of course, this recursive formula can be rewritten in terms of our probability distribution like this. Then this formula is turns out to be very useful. So here is the result only. One result on asymptotic analysis of our distribution. So we consider a limit n to infinity, but we can consider various limits. But here I consider here let me fix the ratios of parameters. This is n. So we fix ratios n over n, k over n, and take limit n to infinity. And let me use some renamed parameters, alpha, beta, gamma, delta. So these ratios also fixed. And fixing these ratios and under some generic conditions, we have the following form of central limit cell. So to changing the variable x to this linear combination. So we have so the right-hand side means the Gaussian standard distribution. So this is a certain kind of central limit cell. And here the parameter, so some quantity mu and sigma appears. So mu is nothing but the expectation value, and sigma is nothing but the variance. And mu and sigma are given by this a little bit complicated formula. But anyway, mu and sigma are expressed in terms of the fixed ratio alpha, beta, and delta. So this is our central limit cell. And how we find this quantity? We guess these quantities by taking a formal limit of the recursive formula aforementioned. So what we did is that replacing x, the variable small x, by n times t. So t is a new variable, or rescaled variable, and taking limit of naive limit of this difference equation. Then we get some differential equation, and this differential equation turns out to be the one characterizing the Gaussian function. So log derivatives are linear function of t, the new variable. And then this equation will imply this type of central limit cell. And this is a statement, but here is an example of plots showing this central limit cell. So by C and dot, I denoted the discrete distribution, and red or pink line shows the no limit distribution. And I fixed the ratios like this. And the left figure denotes that n equal 100 dots, and then n equals 1000. So, these are dots, but anyway. So, and on the right we have 10,000. So anyway, that the discrete distribution seems to converge into the linked distribution. So I have almost finished my talk. So here is the conclusion again. So we have found a discrete property distribution P, whose PDF and CDF are both expressed by force. And as far as we know, it's such appearance of higher hypergeometric polynomial. Higher means that R plus 1 F R, the R is equal to less than 2. I mean, R equal 1 case is the 2F1 Gauss function, so it is ubiquitous in. So I excluded by standard higher. So anyways, such appearance of higher hypergeometric series in probability theory seems to be new. But maybe I'm wrong. But anyway, we found such a distribution, and we showed some central limit cell distribution. And as I mentioned in the beginning, our paper has various materials, and here are some list of the topics I cannot explain in this book. So if you are interested in some in these topics, please ask me or Hayashi Sensei or Ora Sensei in the evening discussion time. And let me conclude, let me close my talk by giving one open problem. But this is a very naive problem. So anyway, so we started with this particular choice of methods, and we succeeded in the computation. but we do not have a conceptual reason why we could get some nice formulas of this distribution. Here is my very naive question. What property of the state C enabled us to get some nice formulas? Or is there some characterization of this vector among normalized states such that the distribution is expressed by hypergeometric groups or polynomials? So anyway, I would be very happy if I can collaborate with you on this problem, on this open problem, for example, in future collaboration. So thank you very much for your attention.
Thank you very much for your talk. We are perfectly on time, so there is time for questions or comments.
Hi, this is could you say?
We cannot hear you very well. The audio.
The applications for quantum information.
The audio is very unstable. Could you please post your question on the chat? Thank you.
Just a little about application quantum information theory. It is a little bit difficult for me. So, we can compute, for example, again, monomer entropy of the distribution and in the limit. And we can how to say, as Hayashi-sensei commented in the middle time that we can say something on the asymmetry of asymmetry as a resource of the quantum information theory. But let me stop here because I'm not, honestly speaking, I'm not so familiar with that topic. I apologize on that point.
Okay, I will explain again.
Sorry. Thank you.
So could you show me the last slide in the first part, final slide in the first part? This one, yes, this one. So now we have this state. This state is pure state. And also this part is invariant with respect to the permutation. This part is somehow not invariant. So this has a asymmetry on the permutation. Now we want to consider its tensor product. Of course, how about the asymmetry of the whole state? So in that case, we consider permutation group on the N. And this one is permutation group for N minus K and K. This part is
K.
And this one was N minus K. Now we want to consider this one. But that, so this one corresponds to the average of the, this one corresponds to the phonema entropy of average of that state by application on the permutation group. That phonema entropy can be given as this X because our result has a central limit theorem. So then that X is almost converges X over N. X over N converges one element. So this one converts to some probability P. So binary entropy of P gives us that kind of phonema entropy. So originally, this one has an entropy, maybe somehow K, L over K, entropy of L over K. But finally, we have an entropy of N over K, N over X. So this one is expressed our phonema entropy. And also, we can consider another problem. For example, we consider application permutation. So if we have this state and our coding system only applied, only given by application permutation, in that case, how much state can be distinguished? We can consider that problem. This is a slightly different problem. And if we focus on the only some rough asymptotics, so that fundamental entropy gives that solution. But if we want to consider that problem more carefully, so in that case, we need to consider second order asymptotics. To discuss that second order asymptotics, we need to consider limiting behavior of this X. So in that case, we have this Gaussian. So Gaussian probability express the second order behavior of that problem. This is the meaning of in the quantum information.
Thank you for the comment on that.
Any other questions? Okay, if not, I would like to thank the speaker again.
Thank you for the attention.
And so what do we do? So the next chair will be Professor Yanagida, right?
Yes. Yes.
All right, so I will leave it to you.
We have a few, 5 or 4 minutes so break. And
Yep.
we'll start at 4 o'clock in Japan time.
Hi, should I share screen now?
Please share screen.
Okay. You can see the screen?
Yes, good. So it's now to restart. So it is a great pleasure for me to introduce Professor Ziwen Liu of Perimeter Institute. And the talk title is No-Go Theorems for Quantum Resource Purification, Universal Theories and Practical Application. So please start.
Okay, thank you very much for the introduction and the invitation. It is a great pleasure to speak here. Today I'm going to tell you about our recent work on the general fundamental limits to the tasks of purifying noisy quantum systems and their practical applications. We actually have a series of papers on this topic. The first one is from 2 years ago and is already published. This first put forward the no purification theory. And the second paper is a more recent follow-up, which completes the picture for channel or dynamical resource theories and also discusses more applications. This is joint work with Kun Fang from Baidu Research. Okay, so here is an outline of the content. In the first part, I plan to introduce the most general form of the theory, and then in the second part, I'm going to talk about the concrete applications. Our general results are bounds on the accuracy as well as the efficiency for very general resource purification tasks in both state and channel settings. And we will introduce two different approaches to understanding this no purification phenomena and deriving lower bounds. We also looked into the applications to a series of very important practical tasks in quantum information processing, including magic state distillation, quantum error correction, circuit synthesis problem, and also quantum Shannon theory. In this talk, I plan to rather quickly go through the general theory and maybe say a bit more about the implications to, in particular, magic state distillation and this quantum error correction problem. In particular, I also hope to additionally overview some other recent progress in this very interesting covariant quantum error correction direction, which is deeply connected to many areas in quantum information and physics. Okay, so the key problem we would like to address by this work is noise, which is a big obstacle that prevents us from already realizing the advantages of large-scale quantum computation and other technologies. The noise is also a problem in high-precision scientific experiments. This is because quantum systems and quantum information is intrinsically very susceptible to all kinds of noise effects, such as undesirable interactions with environments or imperfect controls or unstable memories and so on. So mathematically, the noise effects generically make the ideally pure quantum systems mixed states, so that certain quantum information might be lost, or and the systems are going to become unreliable or lose their power. Our community has been developing and improving many different methods with a general aim of reducing the noise effects or purifying these noisy quantum systems, such as quantum error correction, error mitigation, distillation, and many others. But so far, there's not much systematic understanding about their ultimate performance in practice, and this is what we hope to address. Another notion that we want to introduce is the notion of quantum resource theory. We learn from economics that things acquire resource values when they're useful and hard to obtain. Well, in our physical context, the practical or experimental setups will always place certain constraints on what you can easily do to the quantum systems, and these constraints will induce certain quantum resource features. There are many interesting and very important examples in quantum information. such as the very well-known case of entanglement, which is induced by normally by the local operation and classical communication restriction in the distant lab, so-called distance lab paradigm. And also another important case, which is particularly important for quantum computation, is the case of stabilizer or Clifford group constraints, which induce the notion of magic states that are a very important resource for realizing the computational advantage. And of course, there are many other different forms of quantum resources that can emerge from different contexts. And the manipulation of these different forms of quantum resources actually underlies all kinds of quantum information processing tasks, since they can often be understood as the origin of the quantum advantages of these tasks. Then the so-called quantum resource theory provides a very general language to characterize and study the manipulation of different quantum resources. A certain quantum resource theory is defined by the sets of free states and free operations. And here we only care about one golden rule of resource theory, of the definition of a resource theory, which is that any free operation must map a free state in the theory to another free state, or any free operation does not generate any resource. In principle, the definition of these components, the free states and free operations, can be very flexible according to the scenario that you care about. But the point is that any non-trivial definition of free operation, well, any non-trivial free operation should be contained in this non-generating set, because if your operation can generate a resource from scratch, then the theory will become trivial. Or in other words, what cannot be done, or the no-go theorems under this golden rule, is considered impossible in all non-trivial theories. So here, what we are going to consider is this very general task of transforming a noisy or mixed resource state to some target pure resource state by free operations, maybe probabilistically, and some error could be allowed. Here, technically, we're considering this so-called one-shot setting, or namely, there are only one or finite copies of rho, in contrast to the infinite IID copy setting, which is conventional in information theory, but impractical in some sense. Later, we will discuss the extension to channel theory of this task. And as we'll further see, many important tasks in practical quantum information processing may take such a very general form. And what we will show is that there are very universal no-go theorems, or namely lower bounds on the error on such kind of tasks that apply to any well-defined resource theory for any pure target resource state, and using any free operation or free manipulation. So a key point of our theory and results is that they are very versatile, and can be adapted to a broad range of problems. Or as another quick recap of the important features of our setup, it concerns the important practical problems of noise, restrictions on the manipulation you can do, and the finite resource assumption altogether, and from a pretty general standpoint. Okay, now let's see the first proof idea, which can be explained by resource measures. For meaningful resource measures, the most basic property is the monotonicity property, which really means that any resource measure should not increase under free operation. This is very intuitive because your free operation is not supposed to increase the value of any meaningful resource measure. for example, here the resource measure is a map from the state to a real number. For example, the entanglement, you use entanglement entropy to measure the amount of entanglement, and therefore, different monotones, different resource monotones will restrict different partial orders on the states. Then this means that as long as you find some resource measure, then any state that takes a smaller value of this resource measure will not be able to transform to a state with a larger value by any free operation. Here, our first idea is to consider a very special monotone induced by the so-called quantum hypothesis testing relative entropy, which takes this following form, and it is actually an operator smooth version of the so-called mean relative entropy. The key property is that because this divergence obeys the data processing inequality, so when we define the resource measure by minimizing over free states sigma, this will give us a resource monotone. And this quantity from this paper actually arises from the one-shot distillation rates in general settings. Now to get some intuition about why this monotone is particularly useful, let's set this smoothing parameter, this epsilon to 0. And then this P will become a projector onto the supportive rho. And we can see that this resource measure will take 0 value on noisy states, but it is bounded from below for pure resource states. And also the smoothing procedure guarantees a good continuity of this property. So we can see that in the vicinity of noisy states, this particular resource measure will take a small value, while in the vicinity of a pure resource state, it takes a larger value. So this monotone will restrict the possible transformation of noisy state to pure state by any free operation. And then we can derive a lower bounds on the error by analyzing the detailed behaviors of this quantity. Also know that with a little tweak, we can also deal with the probabilistic transformation case, which is important in, for example, the magic state distillation problem that we will see. So the overall result looks like this. So this is the form of our bound, which depends on the minimum eigenvalue of the noisy state, as well as some certain property of the target pure state. The result can be represented by this forbidden regime of the achievable accuracy and the success probability. The result looks like a uncertainty relation between the accuracy and the success probability of any transformation by free operation. So a conceptual message here is that perfect resource purification is impossible even probabilistically in general cases. Now, before we have seen the most general error bounds, and they can actually be applied to this more widely studied distillation setting. Here, one roughly intends to extract a certain high quality resource state from a larger number of noisy initial state. And now we are interested in the number of copies n needed to achieve some desired accuracy for some target pure resource state, and this minimum number n will characterize the cost or overhead of this distillation task. Now our error bounds can be translated to bounds on this n. In particular, in the small error limit, we obtain that n will scale at least logarithmically in the inverse error. And this, in some sense, reveals a fundamental price for fault-tolerant quantum computing and other quantum technologies that that is based on distillation, as we will discuss in a bit more detail later. Okay, so before introducing the second approach, let's define an important extension of the state resource theory framework, where now the resource objects can be quantum channels, and the manipulation now are described by channel-to-channel maps or supermaps. This generalized framework is necessary to discuss, for example, Shannon theory and circuit synthesis problem, and it is under a pretty active study in recent years. So here in particular, the counterpart of the purification task is now to simulate a unitary channel, or becomes the unitary simulation problem, and the input are noisy channels. A key subtlety of the channel theory compared to the state theory is that now multiple inputs of channels can be composed in inequivalent ways, such as in parallel or sequentially or adaptively or in very complicated ways. But while for state theory, the many inputs can always be represented by a large state given by a tensor product. But now the tensor product structure for channels only really gives you the parallel usage of multiple channels. So now the generalized version of the purification task for channels is to transform multiple channels, which can be consumed in different ways as introduced above, to some unitary resource channel. Now let's go on to see another way to unravel the no purification phenomena, which is even simpler. It is now it is based on decomposing the noisy input state into a probabilistic mixture of a free state and some other state. And now notice that by the golden rule, the free component in the input will remain a free component in the output. And therefore, the output cannot be exactly the target pure resource state. Or more specifically, by quantitatively tracking the behavior of this free component, we can obtain new error bounds, which may depend on the size of the free component. If you see the new bound here, now the difference from the previous approach is that the minimum eigenvalue is replaced by this maximum size of free component. This quantity actually upper bounds the minimum eigenvalue, so that this bound is in some sense more powerful. Furthermore, in certain cases, we can show that this lower bound is tight. So this diagram demonstrates a very simple case of qubit coherence theory. We can see that for any strength of depolarizing or dephasing noise, the lower bound obtained by this method is actually tight. It can be achieved by a certain free map. This method is also discussed in this concurrently posted paper by Regular and Takagi. So if you want to see more details, please also refer to that paper. Okay, maybe let me make a quick pause here, because now in the second part, I'm going to go into the applications.
So is there any comments or questions?
Can I ask one? It is Francesco Buscemi from Nagoya.
Hi.
Hi. I wanted to ask you something about this morphism picture for free operations, like considering the largest set of maps that do not bring free objects outside the free set.
Yeah.
So there are some situations in which these free maps are not very nicely behaved. For example, I'm thinking about like resource theory of bipartite entanglement. There you have that the swap, for example, is a free map in this sense, but the swap can also create entanglement if you have extra systems, like you can imagine that it's performing entanglement swapping between two parties. And so do you have an idea of how to implement this notion of being completely free, like maps that are as large as possible, but even with respect to all possible compositions of these free sets?
Yes.
See what I mean? Mm-hmm.
Yeah, I hear the question. This is a great question. So here, as you said, the complete version of free operations is always contained in this non-complete version, right? Yeah, and indeed, as you said, in some case, the larger set always contains some unphysical free operation. But here the point is that because our main focus is on the no-go theorems, so we can deal with the larger set only, and this no-go theorems will directly apply to these smaller sets. So
sure, I see. Mm-hmm.
Yes, yeah. So that's why we want to say the no-go theorems are most general under these smallest assumption or biggest free set. But indeed, what you said is the problem, is an important point. And if we want to discuss achievability, then of course we want the operation to be physical. But this is in a opposite direction.
Thank you.
Yes.
Is there any questions or comments? Is it okay? So then please restart and proceed the second half.
Okay, so now let me start the second half. Here, let's see some applications to practical problems. So first, let's look at magic state distillation, which is an important approach for fault-tolerant quantum computing. So here the idea is that the Clifford operations are easy in the sense of fault tolerance, but this set of operations is not universal. This can be reflected by the fact that this class is classically simulable. So you need to introduce some other component to achieve universality. And a standard scheme is to distill high quality T states offline and use these gadgets to emulate the action of a T gate in a Clifford plus T circuit, and then you can achieve a universal quantum computation. And as well as these input T states are of sufficiently high quality, then we can expect the whole computation to have low error. The magic state distillation is the dominant source of the resource cost in this pretty nice scheme. So understanding the achievable efficiency of magic state distillation is very important. Okay, so a common formulation of the magic state distillation task is as follows. The input is n copies of the noisy state's row, and the goal is to output with probability p some large state where each of its marginals is sufficiently close to a T state. Now, the question is how large the overhead n has to be. The n is defined in the above by the minimum number of copies you need to achieve this target. And here are our specific bounds for magic state distillation, which are actually obtained from the general lower bounds we introduced above. As you can see here, n indeed scales at least logarithmically in the inverse error of 1 over epsilon. and the noise strength of the input states is encoded in these bases of the logarithm. Now let's compare our lower bounds with the efficiency of magic decision protocols in more concrete terms. The mostly studied protocols are based on using a stabilizer codes and reiterating the error correction process until reaching the target error. And the key parameter, the key figure of merit characterizing the efficiency is the exponent in the average overhead n over m, where m is the size of the big output states, or roughly the number of target t states. Then in code language, our lower bounds have two key implications. The first one is that any sub-logarithmic protocol, such as the recent breakthrough protocol by Hastings and Ha, they must have exponentially diverging output size. Or in some sense, although the average overhead of such protocols can be considered low, the overall cost could blow up even when you only need, for example, a small number of T gates. And then the second one is that for a large class of codes that satisfies the condition k smaller or equal to d, or indeed such as k equals 1 code, the average overhead indeed has a lower bound 1 on the exponent. The next interesting application I hope to talk about is the quantum error correction problem, where the encoder and decoder are now subject to certain types of constraints. The important examples are stabilizer code, which needs no introduction, and also the covariant codes, which we want to discuss in more detail here. Here, the key observation is that such constrained error correction tasks can be formulated as purification in both the state and channel setting. In the state setting, the purification task is on the decoder. Here we have a noisy physical state, and of course the target is to recover the pure logical state. And as long as the decoder is subject to resource theory constraints, then it falls into the formulation of the purification task. And also more generally in the channel setting, now the task is to simulate some identity channel by some noisy channel here. Okay, so here let's discuss a little bit more about the case of covariant quantum error correction, which has emerged as a quite widely relevant and important topic in quantum information and physics. Here, the codes are subject to symmetry constraints that the encoding must be covariant with respect to symmetry transformations. Or in other words, you first encode and then do the symmetry transformation on physical systems. It's equivalent to you first do the symmetry transformation on the logical system and then encode. So there are many strong motivations for caring about covariant quantum error correction problem. So first of all, the Easton-Kneel theorem, which is an important result for fault-tolerant quantum computing, is closely related to this formulation, as we will see later. Also, it is related to error correcting physical or such as reference frame information. And this problem is also realized to be very important in many areas in physics, such as quantum gravity, holography, and condensed matter physics. Now let's see how the no purification story says about the covariant quantum error correction problem. So first, note that here we mainly consider continuous symmetries, which are associated with conservation laws. And then an important lemma is, that we can prove is that under the assumption that the encoder is covariant or respects a certain symmetry, it always holds that some covariant decoding channel can achieve the lowest possible error among all decoders. Therefore, by the insight of treating covariant quantum error correction as a purification problem, we can derive lower bounds or fundamental limits on the accuracy using our resource theory methods, because here the decoder can be assumed to be covariant or does not generate symmetry violations, which means that it satisfies the golden rule of the asymmetry resource theory. The more detailed discussions can be found in paper 2, as well as this another paper with Cici Zhou and Liang Jiang. In particular, in that paper, we studied a very special asymmetry or coherence monotone based on the so-called RLD quantum Fisher information, which takes the following form, where H is the Hamiltonian that generates the symmetry transformation. So the key feature, the important feature of this quantity is that it is bounded for usual noisy states, but takes infinite value or diverges for pure states that is coherent in this Hamiltonian eigenbasis. So by using a similar idea of the first hypothesis testing relative entropy method, we can see that this RLD quantum Fisher information is also able to induce no purification bounds. It turns out that it actually works particularly well for this covariant quantum error correction problem. And the lower bound roughly looks like this, where the denominator is a channel version of the RLD quantum Fisher information. Now I also want to introduce briefly another lens through which we can understand the covariant quantum error correction, which is quantum metrology or estimation theory. This can probably already be seen from the relevance of the certain forms of quantum Fisher information from the previous slide. So here the insight is that a good covariant code naturally provides a good quantum sensor to estimate the parameter encoded in the symmetry transformation, so that we can borrow tools from quantum metrology and estimation, such as quantum information, to analyze the behaviors of covariant quantum codes. So to be more specific, the covariant quantum error correction problem is closely related to the channel estimation problem of this noisy transformation channel, and the existence of perfect covariant code will mean that this noisy transformation can be recovered as a noisy signal channel for which the quantum Fisher information is supposed to have Heisenberg scaling in the larger limit. Then there are no-go theorems in quantum metrology, which says that under this Hamiltonian and Krauss band condition, the above is impossible. Here the case are the Krauss operators of the noise channel. So for example, the E-Sync-New theorem is the case where the noise is local and the physical transformation is transversal. So furthermore, by using a pretty cute trick of reducing this channel to defacing channel, and then analyzing the channel the channel version of the quantum Fisher information, we can also obtain such very powerful lower bounds on the error of covariant codes based on the normal version or regularized version of the normal channel quantum Fisher information. Then we also have a recent result, which can be regarded as a rather strong achievability result of the covariant quantum error correction bounds. Roughly speaking, we consider the model where we generate U1 covariant codes by hard random unitaries that obeys charge conservation law. And the result really says that for certain cases, such random codes almost always saturate the lower bounds asymptotically, or in other words, they are always nearly optimal U1 covariant codes. So here, let me briefly overview the proof techniques since they're pretty nice. First, note that the accuracy or error of an approximate quantum error correction code can be characterized by the complementary channel of the noise and encoding channel. The intuition is that the extent to which the logical information is leaked into the environment will determine the possible accuracy of the recovery. Then for this U1 covariant case, what we found is that the error can actually be broken into two parts. One can be bounded by the partial decoupling theorem, which is a variant of the decoupling theorem with block diagonal structure that correspond to different charge sectors. And the other major part reflects an intrinsic contribution induced by the symmetry constraint, and this part can be directly calculated. Then the result we obtain look like this. We can bound both the Choi error, which is roughly related to the average case behavior of the code, as well as the worst case error. Here, T and A are just parameters of this covariant code model. For certain T and A parameters, what we find is that the leading order exactly matches the known lower bound. So that what we want to conclude is that such random codes in certain cases are nearly optimal. And in fact, the results actually hold for U1 symmetric versions of two designs, namely the distributions on U1 symmetric unitaries that only match the Haar measure to the first two moments. And very interesting unresolved problem I want to mention is the convergence of the charge conserving random local circuits. It is a very well-known and important result that the random circuits converge to T designs in polynomial depth in the case without symmetry constraints. But for our symmetric setting, it seems quite difficult to prove even the convergence to two designs. This problem is potentially important to, for example, black hole and many-body physics, and we look forward to progress on this problem. Okay, so in the paper, we also discussed how our general theory can be applied to quantum communication or Shannon theory and the noisy circuit synthesis problem. Due to time constraints, I shall only do a brief overview of these applications. So for quantum Shannon theory, a core problem is to understand the capacities of quantum channels to transmit information. For instance, for the quantum capacities of noisy channels, we are essentially interested in the optimal rates of simulating identity or unitary channels. So our channel no purification bounds can also apply to this case. Then the different types of capacities, such as unassisted, integument assisted, or non-signaling assisted capacities, they really just correspond to different types of supermaps or combs that are associated with the corresponding capacity problem. And yes, in our unified formulation, they just correspond to different supermaps, as I said. And then the last application we discussed is the noisy circuit synthesis or compiling problem. Here, the problem is to decompose a large unitary, or which may represent some large quantum computation or algorithm. This large unitary encodes it can. The target is to decompose it into a certain set of elementary gates, such as Clifford plus T. And we are essentially most interested in the number of certain difficult gates, such as the T gate in this Clifford plus T scheme. And here, if we consider a practical version of the problem, where the gate is noisy, then our channel no purification bound can induce a concrete explicit lower bounds on the gate count. For example, this diagram shows the lower bounds on the noisy T count for approximately synthesizing CCZ gate. Okay, so let's summarize the work. In this work, we derived a comprehensive theory of universal and practical limitations to purification tasks. We can understand it as a new fundamental principle of quantum mechanics that was not well formulated before, and we found that it has quite profound practical applications to all kinds of problems that's important in quantum information processing. And finally, there's some outlook. Here, of course, we are very interested in the achievability, which means that we want to know in what cases the lower bounds can be achieved, to what extent. And of course, there could be many other practical or physical applications that of such very general theory. Okay, so this is pretty much what I want to talk about today. Thank you so much for your attention. These are the papers that I mentioned today. The first two papers are specifically about this no purification theory. And let me also thank my wonderful collaborators. That's it.
So thank you. Any questions or comments? So can I ask one question or comment? So in some slides, some T design appears, as far as I remember.
Yep.
I'm a mathematician, so but I'm a little bit. I know a little bit about T designs. Could you explain why T designs appears in this context?
Oh, yeah. Maybe I was not clear enough about it. So here, our result relies on this hard random encoding, right? And we derive such lower bounds. But what I wanted to remark is that actually two designs, which of course can be viewed as a simplified version of the hard random unitary, can already achieve such bound. So this result actually holds for two designs. But here we use the hard random language because we can say that, okay, it is a uniform distribution over all kinds of this kind of charge conserving unitaries. So it reflects a typical property of all the unitaries.
So the statement is that the same estimation holds for U1
yes.
symmetric to this itself.
Yes.
And is there any variation, any other variation? So we can consider, for example, we make, this one will be wrong, but so we can consider, for example, other Lie symmetry and other designs.
Sorry, what do you mean? Yeah, of course we can consider other types of symmetry. Yeah, such as more complicated symmetries. Might be
at this moment we don't have.
Yes, our specific results are for the simplest U1 case. Yeah. Yeah.
So it will be difficult to consider more complicated systems. What's the thing?
Yeah, it's supposed to be more complicated, but maybe it's doable. We don't really know.
Maybe doable.
Yeah.
I'm a little bit interested in this topic. Thank you very much.
Thank you.
I have a question. Can I?
Yeah, sure.
So it is related with the question that I asked you before, but now for channels. So we know that for channels also, you can have transformation of channels that are not exactly physical, I would say. Well, some people would argue with this, but transformation of channels that cannot be represented as a circuit. This kind of, I think that they call them a-causal Sheldon transformations or process matrices.
Right.
Things that cannot be divided into a pre-processing, post-processing, and then some side channel. So something that is not representable as a circuit.
Yes.
So the results that you showed us today, they all assume a circuit representation for the super channel.
No. For channel case, it actually doesn't assume a channel form.
Because again, you are interested in no-go theorems, right? Am I correct to think like that?
Yes.
I see.
Yes.
Thank you.
Yeah. If you assume a circuit form, I suppose the state version of the theory should already suffice. But for channel theory, we don't really need a circuit form.
Yeah. Okay. And do you also allow for so here you're always looking at some kind of, I might have missed some parts, so in case I apologize in advance, but are you mainly focused on one-shot theory here? So like given one channel, all right. So in that case, so the super channels are essentially, oh, but you say that you also take into account super channels that are not circuit, because if not, one could say this is just coding, right? I mean, we're just giving a new name for something that is known since 1948, no?
Right.
Like a pre-processing, a post-processing, and some side resource that can be signaling or no signaling, right? So
yes.
Name super channels sometimes in an inappropriate way, I would say, because we already have words for that, and it's called coding, right?
Yeah.
So when super channels become a new thing is when you have either more than one uses of channels so that you can put boxes in different places in your circuit, or when you consider things that are not circuit themselves. And this only happens in quantum theory.
Yes.
Okay, this was more than a question, was a small comment, but
right. Yeah, it doesn't assume such form, but you're definitely right that we're looking at the one-shot setting, because in the asymptotic setting, the rate is just not determined by anything like hypothesis testing, relative entropy.
Right.
For example, in entanglement theory, you know that it's determined by the relative entropy of entanglement, something like that. Yes. So in the asymptotic setting, there is not really such no purification phenomena. It doesn't really distinguish mixed states from pure states or noisy channels from unitary channels.
Yeah. Okay, thank you.
Thank you.
Is there any other questions? So then let us thank Professor Stephen Liu for the wonderful talk. Thank you.
Yeah, so I think it's a bit early, so should we wait until 4?
Yeah, maybe. There could be people that connect at the time, but it's for me, it's fine also to start right now. I let you and Masahito decide. I will just try to share my slides to see if they work.
Yeah, please.
Okay.
Just a moment. If possible, I want to ask previous talk. So, could you show me the definition part of that random coding, random covariant coding?
Sure. Can you see that? Or do I need to full screen it? Here?
But maybe you have this is definition.
No, I didn't draw the diagram, but the definition is that you have some pure logical state, and you append some ancillary states, and you use a large hard random encoding unitary, which maps the logical state to some large physical system.
But here U1 covariant. U1 covariant means that you have a one generator and you apply that.
Yeah, here U1 covariant means that this encoding unitary is charge conserving. So you have some charge associated with this input system,
Charge.
represented by some operator.
Charge means some generator. So exponential that generator.
Mm-hmm.
Oh. And why you consider that U1 symmetry? Why?
Why? Because in physical systems, it is often true that you have some conservation laws, and so this U1 case is like a starting point.
Maybe you can consider some Hamiltonian, and we make some time evolution. So in that one, okay. And I could not find what is the meaning to design in this context.
It's the same. It's the same as the non-symmetry case. To design means that the distribution will match the hard measure up to the first two moments. So here is the same thing, but we only have this additional U1 symmetry condition. But the definition is analogous.
So that T is number of erasures. So maybe you consider some more physical model.
Yeah. For example, when T equals 1, this is also the case where the Troy error is tight. Then it means that you only erase one of the qubits.
One.
Yeah.
Now you consider only eraser channel.
Yeah. Yes.
Okay. Thank you very much.
Thank you.
So okay, maybe we can proceed to the final talk.
Okay. Okay, shall I start?
Yes.
Yes.
Yeah. Okay, so it is my great pleasure to introduce our final speaker, Professor Francesco Buscemi from Nagoya University. Professor Buscemi has done a lot of important works in quantum information, thermodynamics, resource theories, statistics, and so on. So today, Professor Buscemi is going to tell us about retrodictive thermodynamics and the thermodynamic reverse bound. Please go ahead.
Thank you very much for the kind introduction, and thank you very much to the organizers for having given me the opportunity to present this work here. So it is nice to be the final speaker. Yes, it's good, but it is also bad, you know, because people are tired and the time in the afternoon is approaching dinner time here in Japan. So I will keep it light, and I hope to stimulate some conceptual discussion rather than going into technical details. Actually, there are not many technical details in this talk. It's a bit more about some viewpoint on thermodynamics in general, but in particular also quantum thermodynamics. So this is work that has been spread over 4 papers now. I mean, there are these 4 papers that are connected somehow. Some work with Siddhartha Das and Mark Wilde, and then I work with students of mine, and then final to work in collaboration with Valerio Scarani from Singapore. So I will start from the thermodynamic reverse bound, which is a bound concerning the thermodynamic behavior of open quantum systems. So here we use the textbook formulation for open quantum systems dynamics, where you start with a system that is initially factorized from the ancilla that can be, for example, the surrounding environment, if you want to have this interpretation in mind. And system and ancilla will interact with a total Hamiltonian, which is made up of 3 parts. A part which is the system Hamiltonian, another part which is the ancilla Hamiltonian, and then a 3rd part which is the interaction Hamiltonian. And all these 3 things can in principle depend on time, so they can be driven in time. And with this formulation, you know that still, even though the Hamiltonian is time dependent, you can still define a time ordered unitary evolution. And so you can say that the final state of the system at final time equals tau is obtained by this formulation. And because the initial state is in a product form, this actually defines a map. And we know very well that this map is a completely positive space-preserving linear map that transforms the input, the initial density matrix that describes the state of the system at time t0, to the density matrix that describes the state of the system at final time tau. And a crucial quantity in order to understand the thermodynamic behavior of such a very general system, open system, is given by the system's average energy change, which, you know, considering an approximation for which this interaction Hamiltonian is non-zero only in a small region, and the final time is far away, the initial and the final times are far away from this small interaction region that is in the middle, we can say that with good approximation, the system average energy change is just given by this difference between, so it's this is the final average energy of the system, and this is the initial average energy of the system. I would like to change, sorry, okay. I changed the camera mode, okay. So this is the setting, which underlies, by the way, it's used in a lot of papers about thermodynamics of open quantum systems. So a nice thing that actually we've heard also from Oscar's talk 2 days ago, 2 or 3 days ago, is that this quantity, this system energy change, has a lot of nice interpretations attached to it. In particular, it can be interpreted in terms of information divergence very often. And this comes from this bound. Actually, it is exact, you know, it is the starting point of Oscar's talk 2 days ago. So I used the same notation. So I introduced this delta D, So what it means that you have your process that transforms rho 0 into some final state rho tau, but at the same time, because you have Hamiltonians that are defined at every state, every time, at each time you have the instantaneous thermal equilibrium state, which is this gamma 0, that is the negative exponential of the H0 of the system's Hamiltonian at time t0, and gamma tau, which is the thermal equilibrium state corresponding to the Hamiltonian at final time E equal tau. And this average energy change in the system can be written just by manipulation, the standard manipulation of the terms here, can be written as a difference of relative entropy between the instantaneous state of the system with respect to the instantaneous equilibrium state of the system. So you have that this delta relative entropy D is the difference between this d tau and this d0. Plus, you have some difference in the system entropy delta S. So because in general, for an open quantum system, the difference in entropy delta S can be larger or smaller than 0, there is no direct connection between the, without further assumptions, there is no direct connection between the energy change of the system and the change in relative entropy. However, you can also work out another bound, and this is the bound that we call the thermodynamic reverse bound, because instead of considering the difference between the instantaneous state of the system and the corresponding instantaneous thermal equilibrium state, you can actually keep the system state fixed and somehow pull back with phi daga, which is the Heisenberg version of this CPTP map phi. You can pull back this thermal equilibrium state at time t tau back to time 0. And now, if you do that, the system average energy change is always greater or equal than the difference between these two quantum relative entropy. So in a sense, by using this new way to bound things, you can keep a relation between the average energy change of the system and the difference of two quantum relative entropies that carry with them all the goodies of quantum relative entropy in terms of information geometry, for example. So let us see first how this reverse bound is derived. The derivation is very simple. So essentially, we are going to give a bound on delta S, right? Because the difference between these two expressions for the same quantity, you see on the left, we have the same quantity. The difference is that there is a delta S here. So and we want to address that one. We want to write delta S in a different way. So delta S is this thing, is the difference between the final entropy and the initial entropy. And now you just, add and subtract terms, and you end up with this expression where you have the quantity that appears in the reverse bound plus this quantity here. So the crucial point now is that this commutator between logarithm and phi daga is a positive map. So when applied on a positive operator sigma, positive semi-definite operator sigma gives you again a positive semi-definite operator. This is a consequence of the operator concavity of the logarithmic function. It is only that it doesn't use the inequality, it uses a weaker property of the logarithmic function. But because this is always positive semi-definite, you can just remove it from this equality and get bound. It is always directed in this way, so greater or equal than. So in order for this bound to work, you need some assumptions. Actually, you need a very weak assumption in a sense, because you only want phi daga to be a positive unit preserving linear map. So linearity and unit preservation are guaranteed by the fact that phi is trace preserving and linear, and positivity is given by the fact that phi is completely positive. So actually, this bound would work in principle also for evolutions phi that are not completely positive. You would just require, you would only need a positive trace-preserving linear map to describe your system evolution, and still you would have this reverse bound that works. So this can be specialized to the case in which sigma is equal to the final state phi rho, in which case becomes an extremely strong expression of the general equation of approximate reversibility. In particular, you have that it strengthens considerably the data processing inequality, in that here at the right-hand side, you have the difference between rho and the recovered version of rho using the quantum relative entropy, which is stronger than having a bound in terms of minus log square fidelity that is used in papers about approximate reversibility. So this is particularly meaningful for bistochastic, so for maps phi that are at the same time trace preserving and unit preserving, so that also their Heisenberg dual or trace dual phi daga is also trace preserving automatically. And so this phi daga can actually be seen as an actual channel, as an actual CPTP linear map that corrects, brings back rho to something that is close to rho. So if this difference in entropy is not too large, then you can say that phi daga is a good approximate recovery map for phi. But now this poses the question, so apart from this bound, the interesting point for me is, what is this phi daga here? What is the role of this pullback operation that we do on the final thermal state? What does it mean that we take the final thermal state and we bring it back to initial time? What kind of process is this? So the bound is this one. So here we have something that in general is not a state. So it's going to be some positive semi-definite operator, because phi daga is positive, is a completely positive map, but it is not trace preserving. Therefore, this state is not normalized state, and it needs to be normalized. So by introducing the normalized version of this state, you can rewrite this lower bound as a difference between the relative entropies of between two pairs of states, and an extra term here, which is the logarithm of the trace of this phi daga gamma. So this can be greater or smaller than 1, and so the logarithm can be greater or smaller than 0, depending on the situation. The point is that this term appeared already in many and in a large number of works, especially dealing with fluctuation relations. This is called the efficacy, and it's the log efficacy. And it appeared already in some papers by Sagawa and Ueda when they were considering the efficacy or the efficiency of a feedback protocol to correct a monitored open quantum system evolution. But it also appears in attempts to extend fluctuation relations to open quantum systems. In particular, there is a paper by Albash et al. In 2013, and then a paper about the Landauer's principle for open quantum system by Gould, Paternostro, and Modi in 2015. So this pullback mapping now, which has this kind of normalized version of this phi daga, is CPTP by definition, but in general is non-linear, right? Because there is this normalization factor here. So before going into the rabbit hole of trying to understand what this pullback mapping is actually and how we should understand that, well, it seems to be playing an important role in the thermodynamics of an open quantum system. So what it is, I think it's an important question to ask. What does it represent? How can it be understood and interpreted? So let's see some applications. So the easiest, the most common situation in which you want to consider an open quantum system dynamics and the thermodynamics of it is when you have to deal with erasure processes where now the system is the environment. So you consider the fact that you start from a system that needs to be erased, and this system will interact with an environment whose state is the thermal state, is an equilibrium state, the environment. And the Hamiltonian of the environment will not change, so the difference in free energy is 0. And the change in energy now, because it's change in energy, internal energy of the environment, of the thermal bath, is interpreted as average amount of heat that it is exchanged during the erasure process. And here you see plots that were given at first in this paper by, as I mentioned before, by Gould, Paternostro, and Modi. So their curve is this slash dot curve here in various situations. The blue curve is the actual amount of heat that is exchanged. This is computed exactly with this toy models involving some spin chain in the system. And you see that our bound, this reverse bound that has this extra term, because, by the way, I didn't mention something, but the Gould, Paternostro, Modi lower bound involves only this term here. And here we are able to add an entirely new term, which is the relative entropy between ρ0 and gamma 0. So you see that it is actually always much better than the bound. And also it compares better with the bound involving only the change in the system's entropy, right? You see situations, for example, here, if you change the parameter of this model, you see situations in which the bound involving only the efficacy, the log efficacy, is quite bad, is actually the farthest from the actual curve. The bound involving the entropy change is somewhere in the middle, whereas the bound, our bound, the thermodynamic reverse bound, is always the closest one to the actual heat exchange. And still, it is written in terms of a difference of 2 quantum relative entropies. So it has a good interpretation. One could go into considering, for example, infinitesimal, see how it is related with change in Fisher information, for example, or, for example, investigate something that Oscar already told us during the first day of this workshop about the speed at which these processes can occur. So in a sense here, the first part of the talk is over, and I would like instead now to adventure myself into the interpretation of this pullback map. So what is that? So I don't know, until now, everyone has very nicely divided their talks into 2 parts. My division is not even because the second part will be longer than the first part. But if there are questions about this first part, that was in a sense the motivation for me to get into the interpretation of the pullback mapping. I would like to ask for questions now, if there are questions about this initial part.
Hi, this is Oscar.
Hi, Oscar.
Hi, yeah, so this is very interesting. Could you just show the definition of the pullback map again?
Yeah, this one. So you have that the thermal state at time tau, which is the final time, is pulled back as if it were an operator using the trace dual map phi daga, which is the Heisenberg version of phi. But then because phi daga is not trace preserving, you need to normalize by its trace, right?
So is this defining the phi dagger?
The phi daga is defined only by trace relation. So the phi, so if you have it, so phi is a CPTP map, right? Mm-hmm. So it will have a cross representation with, for example, EK rho EK daga, sum over K. So the phi daga has EK daga, rho EK. So you just exchange the daga of the Krauss with the direct Krauss. So it is the map that acts on operators usually, but here somehow we are pulling back a thermal state at time tau.
Okay. So this equation basically defines the gamma tilde.
Exactly. Yeah. Exactly. It defines the gamma tilde. And because you see that here, in general, you have this pullback mapping, you see that at the bottom, at the bottom, you have the trace that depends on X. So you are dividing by a number that depends on X. And this makes the map nonlinear. It can actually be thought of as a projection, as a kind of entropic projection of X onto some set of operators, if you like. Like you have something that is completely positive and trace preserving by definition, but non-linear.
Okay, thank you. Yeah, I understand now.
You're welcome. All right, so this non-linearity was very interesting to me, because one can say that in quantum information theory, typically people are not used to see things that are non-linear, but actually in statistics, nonlinear maps are very important in the context of inference. When you're doing inference, when you're doing an update, typically the update is nonlinear. And indeed, if you think about what does the pullback mapping look like, I would say that it looks an awful lot like Basel plus rule for classical probability distribution. So from now on, I will just stroll in the woods of interpretations of these things, right? So first of all, well, the Basel plus rule, what it is, everyone knows what is that, right? So the Basel plus rule tells you that given a prior about your hypothesis, H, and given a likelihood, so given a statistical model that you assume as a stochastic mechanism that associates data to hypothesis, so this is a conditional probability. If you are given some data D, then you should update your prior distribution over the hypothesis according to this formula. And in the middle, you have a proportionality symbol because the posterior distribution, PH given D, should be normalized after that. After you do this multiplication, you should normalize that. And so you have a dependence that is nonlinear. You're normalizing this object exactly as we were doing in the pullback map. So here I'm not going into considering what is this prior, how the prior is chosen. This is a problem that has been beaten to death, and so I will just be using the Basel plus rule as a tool to reason in the presence of uncertain data. So I will not subscribe to any interpretation here. I'm just using it as a tool, and so you can say that I'm going to do some kind of postmodern Bayesianism, right? So I do not subscribe to any ideology behind a Basel plus rule. I'm using it as a tool. So, and as a tool, Basel plus rule is used in Bayesian statistics to solve problems, to provide a solution to problems like estimation and decision, predictive inference, for example, weather forecasts, but also retrodictive inference. And it is something that as physicists, we're not so much used to think about, because in physics, we're typically interested in preparing a system and let it evolve forward in time, so that typically we are used to have a predictive inference approach to physical systems, but there are entire branch of physics that instead rely exclusively on retrodiction, typically astronomy and cosmology. There is no way for us to prepare two cosmological objects and make them evolve, right? We can only passively look at the night sky and wait for data to reach us and retrodict what kind of cosmological event possibly caused those data, right? So retrodiction is nothing weird. It is actually a very well-defined process of inference. It is an inference that instead of going forward in time, it goes backward in time, but it is perfectly legit process of logical thinking. But of course, you can also give like the interpretation in terms of degree of belief to these numbers. So the inverse probability, according to this interpretation, would measure the degree of belief that the rational agent should have in one hypothesis, among other mutually exclusive hypotheses, given the data. But there is one thing that Bayes' rule, as it is not able to deal with. And it is the fact that Bayes' rule is not able to deal with uncertain data. So Bayes' rule only tells you how to update your prior knowledge, given that you observe a well-defined data D among the set of possible data. So if we go back to the formula here, this D, it is a fixed, we can write it as D bar, right? For example, to stress the fact that you are 100% sure that the data you observe is D. But there are situations in which the data you observe or the data on which your inference is based upon do not come to you so neatly. For example, suppose that you are given this picture and that your inference should use as data the license number plate of this car, right? But the picture is so noisy so that you cannot actually say that you are seeing any definite number plate license here, but you can probably give a probability to what you're seeing. So with high well, I don't want to use the word likelihood, but it is very likely that the first symbol here is an A, or at least it looks like an A to me, or maybe an AY, but I cannot be 100% sure that it is an AY. I can only say that, you know, I could, for example, give a degree of belief and to what I'm seeing at this picture, right? So how to deal, so the problem arises as to how to deal with the update in case the data are given to us not in the form of a sharp data, but as a soft evidence. In the literature, this is called update in the presence of soft evidence, when we only have some kind of uncertain evidence given to us in the form of a distribution, probability distribution over the data set. So in order to deal with this problem, we need something a little bit more than vanilla Bayes Laplace rule. We need something that is known in the literature of statistical learning as Jeffrey's rule of probability kinematics. So we have that the vanilla Bayes, as I said, it is something that tells you how to update your prior pH given some certain data P. So now what we want is a formula instead that updates your prior on the hypothesis H given a probability distribution over the data. And the formula that was proposed by Jeffrey in 1965 looks as follows. So here you put the inverse probability that you would have from a vanilla Bayes rule, but now you use it not as a conditional probability, but you use it as a channel itself that propagates your belief on the data back onto the hypothesis. So you can expand this and you see that, you know, this is just Bayes Laplace rule, this orange part. So actually Jeffrey's rule was introduced at the Hawk in 1965, but it can be proved in Bayesian networks by using Bayes Laplace rule, vanilla version, plus Pearl's method of virtual evidence. So Pearl's method of virtual evidence tells you that, okay, you might not be sure about your data D, but anyway, you got some piece of evidence that it is sure. So for example, you can say, going back to this picture, you can say that I'm not sure about the driving license plate number here, but I am sure about the data, about the pixels that make up this picture. So then you can say that you know, you have an extra node in your Bayesian network that represents the data that you get from the picture. And these are well-defined now, so they represent a well-defined piece of evidence, hard evidence. And then you use Bayes' Laplace rule to backpropagate this onto the number plate license. And then you can apply again this Bayesian network backpropagation technique to have your update in the presence of soft evidence on the driving plate number. And this would coincide with Jeffrey condition. So Jeffrey conditioning can be assumed, but can also be derived as a theorem. So now, given that now we know what is a Bayesian retrodiction, so Bayesian retrodiction uses this extended Bayes Laplace rule that is called Jeffrey conditioning to construct a channel now. These numbers constitute a channel that is able to backpropagate your soft evidence on the data onto the hypothesis. So now let me go back to thermodynamics and let's see situations in which this kind of idea, like this kind of reverse process, kind of pullback or something that happens reverse in time appears. And these reverse processes lie at the core of fluctuation relations that can arguably be considered to be the single most important advance in non-equilibrium statistical mechanics in the past 20 years, conceptually speaking. Fluctuation relations and balance equations were there already since before, but I would say that especially after the famous Jasinski equality and Crookes fluctuation theorems in the late 90s, there's been a boom in applications of these ideas because they became extremely clear. So let's see where the reverse process enters the second law. So we have to imagine a forward process and a reverse process that looks similar, very similar, but in a sense, they happen in reverse. So you have a forward process that you can imagine, like this is the simplest example of such a process. You can imagine that you have some mechanical system, some gas, for example, some ideal gas that is enclosed in a piston, and it initially is in thermal equilibrium with some surrounding environment. Then you isolate your system by putting some adiabatic walls around the piston, and then you plunge the piston in. So this will drive the Hamiltonian of the system, and correspondingly the state of the system will be driven away from equilibrium, right? Because there is no possibility for the system to equilibrate with the thermal environment, surrounding environment anymore. So this is the forward process. Given the forward process, it is very natural in this situation to consider a reverse process, where you start with your system in the compressed piston, again in thermal equilibrium with the environment, and now instead, after the adiabatic isolation, you pull the piston out. And you can look at the work statistics here because we're assuming a small system here. And so everything is going to follow the rules of stochastic thermodynamics. So sometimes you will get more work out of it, or sometimes you will need more work to plunge the piston in a stochastic fashion. So what you're really interested here, you're interested in the distribution of work for the forward process and the distribution of minus work for the reverse process. And central here is this theorem by Crookes, dating back in 1999, that tells you that in very general situations, we will see later on the assumptions under which this fluctuation theorem holds. The ratio between these two probabilities is equal to the exponential of the dissipated work. So you are in a situation like this. You can actually do the experiment, and the experiment has been done with beautiful plots, by the way. So you can actually sample from the forward process, and you will have some distribution for the work in the forward process. And you can then sample from the reverse process, and you will have some probability distribution of the work for the reverse process. Now you plot not the work for the reverse process, but you plot the minus omega for the reverse process. And you will see that however these things are distributed, they will intersect exactly and only when the work is equal to the difference in free energy. Which means essentially they will intersect only when this process was essentially a quasi-static process, where you were lucky enough to use the minimum work possible. And this is central in our understanding of thermodynamics, not only macroscopic thermodynamics, but also its underlying stochastic thermodynamics, because Crookes fluctuation relation implies Jarzynski equality, which implies the second law of thermodynamics. So now the question that puzzled me here was, well, why this holds, right? So we know that the second law of thermodynamics is very general in its applicability. Actually, many people argued for the second law of thermodynamics to be very special amongst the laws of physics. There is a famous quotation by Sir Arthur Eddington that says that, you know, you might have a theory that violates Maxwell equations, and that could be okay. I mean, we should check your theory against experimental validations. But he says, if your theory violates the second law of thermodynamics, I can only imagine your theory to collapse in the deepest humiliation, right? So it seems that the second law is something that goes somehow beyond physics, right? However, this theorem requires a physical model underneath. And the usual explanation for the validity of Crookes' theorem, and hence of Jarzynski's relation, and hence the second law, are the validity of two assumptions that are satisfied at equilibrium, or are typically accepted to be satisfied at equilibrium. The first assumption is thermal equilibrium, so that we know that the initial distribution has this Gibbs form, depending on the energy of the microstates. And we know that thermal equilibrium can be justified in terms of inference, right? Because you can use the Jane's maximum entropy principle. So the thermal equilibrium is the least committal distribution that is compatible with your data if your data is given in terms of an average system energy. So thermal equilibrium is very sensible. It is something that indeed can be explained beyond physics. It can be explained by a notion of consistent logical inference. But then there is another assumption for the validity of Crookes' theorem, that is microscopic reversibility, that is extremely closely related with the condition of detailed balance. It's not equivalent, but they are often mistaken one for another. And anyway, they are very closely related. And macroscopic reversibility is defined as the property that molecular processes and their reverses occur at the same rate. So it really seems like that fluctuation relations, and therefore the second law, require the existence of some microscopic balancing mechanism at work that keeps the forward process rate equal to the reverse process rate. But this is something that I personally don't like. I couldn't understand. I mean, this wouldn't justify the special role of the second law, right? So here, again, I would like to follow a hint from Edwin James, who wrote in this paper dating 1984, which is called, I think, Predictive Statistical Mechanics. So he writes this very nice sentence that to understand and like thermodynamics, we need to see it not as an example of the n-body equations of motion. So we shouldn't think of thermodynamics as something that occur because of some microscopic mechanism or the form of microscopic Hamiltonians, but it should just arise as an example of the logic of scientific inference. And we know that Edwin James considered logic or extended logic essentially, probability theory as extended logic. So everything should be based on the Bayes-Laplace rule, because Bayes-Laplace rule essentially guarantees that you are thinking logically, that you are not, you cannot attacked by some kind of Dutch book argument. It only, essentially Bayes-Laplace rule guarantees consistency of your logical inferences. So the first idea that we had, so now this is the second part, so this is joint work mostly with Valerio Scarani in Singapore. The first idea is to see the reverse process as Bayesian retrodiction instead of an actual process that is going on inside your piston. So how to construct the reverse process from retrodiction? So first of all, why retrodiction and how it is related with the pullback map that I said before? Because now the pullback map seems to be a form of retrodiction, logical retrodiction, rather than a physical process. It is looks more like a sort of Bayesian update or Bayesian retro update. So how do you construct the reverse process using retrodiction? So first of all, you can say that physics gives you the setup. It gives you the stage on which the process happened, but rather than having any actual process going on, you are inferring the processes. So physics sets the stage, and it sets the stage by giving you the stochastic transition rule between the state, the microstate of the system at time t0 x, and the microstate of the system at time t equal tau y. And by giving you the stochastic transition rule, also you can say that it gives you a set of steady states that can be one or many, depending on your statistic transition rule. So say that a steady state for you is this SY. So now you do Bayesian inversion at the steady state. Bayesian inversion is just by applying, the product rule, so that you have the definition of this phi hat, which is your retrodiction at equilibrium. Why at equilibrium? Why you use the steady state? Because typically fluctuation relations are meant to be fluctuations around equilibrium, and so it is very natural to do your Bayesian inversion at the steady state. This will define some process, reverse process phi hat, for which the input label is y, which is the state of the system at later time, and the output label is x, which is the state of the system, the microstate of the system at the initial time. So an important thing is that the ratio, if you define the reverse process phi hat in this way, the ratio between the forward process and the reverse process is given by the ratio of the steady state. It depends only on the steady state you chose, S. And now you give two priors, one prior for the predictor, which is Px, and another prior for the retrodictor, which is Qy. So you have a reference state with respect to which you do the Bayesian inversion, which is the steady state, Sy. And then you have the prior, the retrodictive, the predictive prior, P, and the retrodictive prior, Q. And using these two priors, you define the two processes. The forward process, which is the prediction, and so it uses the direct, the forward process phi of y given x and some prior px, and the reverse process, which is the retrodiction, that instead uses the retrodictive prior q and the retrodicted process phi hat. So just to give you a picture, so you can imagine that you have the two processes, the direct process and the retrodicted process phi hat. If you enter with the steady state, the two things will coincide. So the two agents, the predictive agent and the retrodictive agent, will agree, right? If you give them as prior knowledge the steady state. But if their prior is out of equilibrium, is not the steady state of the process, then the predictor and the retrodictor will disagree. And you have a situation of asymmetry. that can be called also irreversibility, or better yet, irretrodictability. So here we are using a nomenclature that was introduced in the 50s by Satoshi Watanabe in a series of famous papers in which he considered the symmetry of physical systems. And he has the third part, which is called prediction and retrodiction in physics. And he actually makes a point about using the notion of irretrodictability instead of the notion of irreversibility when dealing with stochastic statistical mechanics. So we are following Watanabe nomenclature here. So then the second idea, but this is something that is done routinely in the literature of fluctuation relations, is to say that fluctuation relations are measures of statistical divergence between the forward process and the reverse process. In particular, you can take the relative entropy. In this case, you have that the relative entropy between the forward process and the reverse process given by the average over the forward process of this number here, which is minus logarithm of this ratio. But more generally, and this is something that is not done typically in the literature of fluctuation relations, you could use any, for example, F divergence, where F is some function of this ratio, and then you average over F. But the point is that you can consider this, of which you take the average, as the fluctuating variable, right? And because when you take minus logarithm, this is the entropy production, you can call this F entropy production, and then introduce formally, well, this variable is a discrete variable, but you can formally introduce probability density of some variable omega by using Dirac delta functions here. And you will see that the average of this omega of the forward process is the F divergence between PR and PF. And then, well, you can, assume something just for fun. Let's see how you get back to Crookes fluctuation theorem for general F divergences. You can assume that F is invertible, and you can directly obtain an F fluctuation theorem, where you have now that the ratio between the forward and the reverse process is given by this F to the minus 1. So for example, if F is minus logarithm, for which you get the relative entropy, F to the minus 1 is the negative exponential. And so you go back exactly to Crookes relation, which implies, of course, Jarzynski relation as well. So these things about F divergences and F fluctuation theorems are discussed in these papers, but these are not so much central. Rather, I would like to show you how previous results are actually compatible with retrodiction. So you're not doing anything new, you're just changing the interpretation. You're starting from the idea of retrodiction that does not rely on any assumption of microscopic reversibility or any assumption of the tail balance, but still you can work out fluctuation theorems. And these theorems recover fluctuation theorems in particular physical scenarios. For example, if your system is a driven closed system, right? So you have a system that is closed, is adiabatically isolated, there is no exchange of heat with the environment, and the protocol is a protocol that drives the Hamiltonian of the system from H0 to H tau. Then, because the flux of the macrostates is reversible here, you have a closed system, your stochastic transition rule is actually a deterministic transition rule given by some delta of y and some y that depends, which is a function, a one-to-one function of the initial microstate x. So in this case, it doesn't matter which kind of reference distribution you consider. When you do Bayesian inversion here, you will always have that the reverse distribution, the reverse transition rule phi hat is given by this. So you just exchange the input with the output, right? Because this is a deterministic evolution, so it's just a permutation of microstates. And so it is very natural to see that Bayesian inversion gives you exactly the inverse permutation. It's compatible with the inverter. And now, if you give if you fix the predictive prior and the retrodictive prior to be the thermal distributions, the thermal equilibrium distribution with respect to the initial Hamiltonian and the final Hamiltonian, then you are led to the following calculation. So the ratio between the predictive process and the retrodictive process, again, factor out in this way, so that you have a change in equilibrium free energy, delta F, and a change in the internal energy of the system, which, being the system adiabatically isolated, can be completely ascribed to work done by the driving protocol onto the system. And so you get exactly, literally, Crookes fluctuation relations also with this retrodictive narrative. But also you can apply this retrodictive narrative to more general non-equilibrium steady states. So suppose that your stochastic process in some, arbitrary steady state Sx, but again, you keep the predictive prior and the retrodictive prior to be the thermal equilibrium distributions. You plug, these assumptions into the Bayesian retrodiction machinery, and what you find that automatically these numbers appear, and these numbers are exactly actually what are called the non-equilibrium potential. See, for example, this paper by Manzano, Parondo, and Horowitz, 2015, but also the famous paper by Hatano Sasa, 2002. So if you compute the fluctuation relation for this fluctuating variable that includes the internal energy and the change in the non-equilibrium potential, you get an exact fluctuation relation. But if you don't use this one, because you don't use Bayes' Laplace rule to construct your reverse process, you end up with something that does not sum up to 1, but sums up actually to something. And this something is the efficacy. So we see that the efficacy is something that appears when you do retrodiction in a wrong way, right? Without using Bayes' Laplace rule, but using some ad hoc assumption, ad hoc process, inference rule. So we see that non-equilibrium potential also that were introduced ad hoc in order to keep, these fluctuation relations consistent, are understood here as remnants of Bayesian inversion. So you do not need to introduce non-equilibrium potential by hand, but if you use Bayes' Laplace rule, non-equilibrium potential will just emerge naturally from your equations. So now we saw a couple of examples that tells you that known relations, fluctuation relations, are compatible with Bayesian inversion. But is it a necessity? Okay, and here is a simple argument that tells you that in many situations, yes, this Bayesian retrodictive narrative is necessarily present if you want your fluctuation variable to satisfy some desiderata. And the desiderata appears as follows. So let's consider the usual scenario in which you are computing the relative entropy between forward and reverse process. And now let us impose that the fluctuation variable is local, so that this omega can be written as the difference of some function g prime computed at macrovariable macrostate y, and some other function g computed as initial macrostate x. So by assuming, so local because it depends only on the marginal of this function, it does not depend on the correlations between x and y. This is the case, for example, when the fluctuating variable is an entropy production, or more correctly saying a non-adiabatic entropy production. So then by imposing this, and factorizing here the two priors that are already in this form, you have that this condition implies this for the ratio of conditional probabilities, whatever they are. So here, I'm not taking the reverse to be the Bayesian reverse already. Here, the reverse process is just some process that I call it to be the reverse process. So this is a point to be stressed. Now, the reverse process is just something I arbitrarily call to be the reverse process, but I require this ratio. So I require the fluctuating variable to be a difference of local functions. So if this is required, then I can see a chain of implications. In particular, by summing over X, this, I don't know what it is, but it will be a well-defined conditional probability. So summing over X will give me 1 for all Y. And so I can reach the conclusion that the transition rule that governs the reverse process must have the form of a Bayesian retrodiction done with respect to the forward process. So the conclusion is that a Bayesian inverse-like form for the reverse process is inevitable if we want a fluctuating variable to have a local form. Finally, what about the quantum case? Well, now that we see that we have understood that the reverse process is retrodiction, then we can say that the quantum reverse process is what you get from quantum retrodiction. And what is the thing that you get from quantum retrodiction? So I will go quickly through these slides. So suppose that you have some quantum inside process. So inside this input-output process, there is some quantum mechanism going on that can be seen as the preparation of states rho X, then some CPTP map that propagates the states towards a final measurement given by POE and PY. So let Sx be an invariant distribution for this stochastic matrix. And then you can just apply the formalism of quantum retrodiction that tells you to construct the state sigma, and then you have the corresponding retrodicted state, retrodicted measurement. So the retrodicted states depend on the measurement. The retrodicted measurement depend on the prepared states. And the retrodicted evolution is the Petz reverse here. So Bayesian inversion works seamlessly also in the quantum case. And this is interesting because until now, quantum fluctuation relations were known to involve the Petz reverse map, but there was no general reason why the Petz reverse map should appear in quantum fluctuation relation. Here we understand, actually this argument can also be generalized to a fully quantum case where you don't have this classical input and classical output, that you just look at the quantum process as a whole. Petz map arises from the idea of quantum retrodiction. So it is not something that you use just because you get equations that reminds you Jarzynski equality or Crookes fluctuation theorem, but it is something that it has to do with the logical foundations of fluctuation relations. So some remarks. Petz recovery maps reduces to Basel plus rule when operators commute, of course. The point is that to a unique Basel plus rule in the classical case, there corresponds infinite possible Petz maps. These are the so-called rotated Petz maps or swivel Petz maps. This is a very important point that points toward the idea that in quantum mechanics, you might have an infinite ways to do retrodictions compatible with the total load probability. So retrodiction, again, always depends on the choice of a reference paradigm. This is true both in the classical case and in the quantum case, but there are exceptions, and exceptions are unitary evolutions or unitary channels, or using Watanabe nomenclature, bilateral deterministic channels, because for unitary channels, there is a unique Petz reverse, and the Petz reverse is U-Daga. And the retrodiction is independent of the choice of prior, and all rotated Petz maps coincide for unitary channels. And for unitary channels, retrodiction and linear inversion also coincide. Whereas generally, retrodiction and linear inversion are very different concepts. Retrodiction has to do with inference, it has to do with learning. Linear inversion instead looks at the map as linear correspondence between input distribution and output distribution. Typically, a channel might have a linear inverse, but such inverse might not be, actually typically is not a channel, it is just a linear map. Conclusions. So final messages. So what I wanted to say, so I started from the thermodynamic reverse bound. That was a kind of very standard thing like calculation and some improvement of known bounds. But then this led us into the rabbit hole of understanding what is this pullback map and how it can be interpreted. And we were led towards retrodiction. So the pullback map is the retrodiction. So retrodiction or this pullback map can be a useful concept in quantum thermodynamics and approximate recoverability. So we save a lot by thinking that the reverse process is not a new process that must be implemented physically, but we can think of it as an update, as a learning process. Then predictive and retrodictive inference provide the logical foundations of fluctuation theorems. So this is for me a very important point, because it makes me understand that not only the equilibrium distribution can be understood only on the basis of logical inference, but also the second law itself, right? Because in the second law, there is the reverse process, and the reverse process is not the physical process that involves a physical mechanism, but it's just retrodiction. So the second law, now we understand why it is special among the laws of physics, because it is not much about physics as it is about logic. So it is something that guarantees that your logical inference process is self-consistent. A clear distinction between mechanical irreversibility and logical irretrodictability avoids unnecessary paradoxes. Like, usually people speak about the Loschmidt paradox, the echo paradox, which is a nonsense because it's speaking about two completely different things. So the thermodynamic irreversibility has nothing to do with the macroscopic reversibility. So instead of using the same term for two different things, I would suggest to use irretrodictability when we are dealing with stochastic processes, and reversibility when we are dealing with the underlying mechanical processes that can be quantum mechanical processes. So division between reversibility and retrodictability. And finally, I would like to remind you the fact that we've seen that quantum retrodiction and quantum fluctuation relations also follow seamlessly using Pet's recovery map that is now understood as a process of retrodiction, of reverse inference. And that's all I wanted to tell you, and I thank you very much for your attention.
Okay, let's give a round of applause to Professor Buscemi for his wonderful talk. Are there any questions?
Yeah, thank you for a very interesting talk. I learned several things. One maybe silly question was, you mentioned how if you have the thermostate, then the retrodictor will agree with the predictor.
Yes.
And can you use, or have people use this to derive the Gibbs state from demanding this?
No, not that I am aware of. Actually, these things are very new. I never found much. There are papers that deal with, for example, thermodynamics of prediction, and this is a paper by Crutchfield, and actually the first author is
Susan Steele, right?
Susan Steele.
Yeah.
But they do things in a very different way. So they are not much interested about the relation between prediction and retrodiction. And so there is no, like, I've never seen, to my knowledge, I never seen the reverse process understood as retrodiction. So this opens up, for example, the possibility of using fluctuation relations for something, for a situation that has nothing to do with a thermodynamical narrative. One could use one could introduce fluctuation relations for, I don't know, learning, for economics, for anything. So,
yeah, that makes sense.
Not that I'm aware of.
Yeah, I mean, so that's also very interesting. But can one? It would be like James's argument for the thermostat has some weird parts, right? Like, why should you maximize the Shannon entropy specifically, for example?
Well, there are some ways to see that Shannon entropy can be singled out as the only function that satisfies some set of desiderata.
I know he says that, but then, so now I'm going off on a tangent, but then, like say Rényi entropies, he would say, okay, if you have these axioms which are only slightly weaker, then you have a wider set of entropies that you could use. But anyway, so my point was that, like, I think there's still a need for conceptually clean and interesting derivations of the Gibbs state and why it's so special.
Thank you.
Can I also ask a small question?
Of course.
Yeah, I'm a bit interested in the Foley quantum fluctuation theorems.
Yes.
Did you mention that you can also get those from the retrodiction?
Yes, that is work in progress.
Oh,
But yes, you can get them. And the point is now that you have to, sorry, let me go back here. So you have to find a situation where the PETS map arises from as the optimal inference you can do backwards in time, right?
mm-hmm.
So that can be the tricky part. But once you have once you can justify the PETS reverse to be actually the optimal thing you can do when you do quantum retrodiction, then the formulas carry through. So yes.
Yeah. So basically, we should look forward to the new paper, right?
It will. I don't know when it will be out. It's
okay,
a work in progress.
I see.
It's not over. Probably there will be some technical glitches appearing at some point, but
yeah, I see. Yeah,
we are excited about that, no? Because that would be a good way also to justify PET's reverse map as, I mean, why it works and why it appears in so many areas of physics. It is not only, it appeared for by PETs in considering monotonicity of quantum relative entropy, but now it's everywhere. It is in the black hole information paradox. It is in many body systems and solid state physics. It is everywhere. Why it is everywhere? Point it is that it is the way in which you do retrodiction for quantum systems.
Yes, wonderful. Thank you. Are there any other questions? If not, maybe let's thank Francesco again for his wonderful talk. Masahiro, are you going to say something?
Not me.
Yeah.
Give some.
Yes, sir. Shall I make a concluding remark?
Yes, please.
Okay. So this is Hiroaki Kano from Nagoya University. I'm supposed to be one of the organizers. So let me make a concluding remark. So this is the end of the first joint workshop on quantum science for the enhancement of the collaboration between SUSTech and Nagoya University. On behalf of organizing committee, I'd like to thank all the participants, in particular speakers, for their inspiring talks. I believe that there have been many fruitful communications during the workshop. And on the other hand, as one of the participants, I'd like to thank Hayashi-san for his effort for making this workshop in the present form. I think his proposal that each speaker takes the chair, the subsequent talk, did actually work. Okay, so my background is mathematical and theoretical high energy physics. So I feel sorry that I was not able to make enough contribution to the program on Tuesday and also today. But I think this kind of workshop is very important, not only for the collaboration between two institutions, but also the communication among various disciplines in quantum science. So let me tell you an example from my area of research. In my opinion, one of the most challenging problems in quantum physics is a quantum black hole. For example, it poses us an information paradox, as briefly mentioned by Professor Buscemi in last comment. So last 2 decades, many people have tackled the problem by idea of holography, which is a kind of bulk boundary correspondence. Recall that it was one of the main topic in the first day. On the other hand, it seems that some recent development on this problem calls for quantum information theory. So this is just an example. Certainly, there should be many challenges which give us a good chance of communication of people working on different disciplines. And also in this respect, it is also important to invite young people, in particular, for example, postdoc and PhD students to our activity. So in any case, it is very important to keep the collaboration of SUSTech-Nagoya, since both have their strengths at quantum science. I hope we can have a second workshop in near future. When the pandemic of COVID-19 is over, we can actually have a real face-to-face meeting both in Nagoya and Shenzhen. I'm looking forward to seeing you again in the next joint workshop. Thank you very much for your attention. Oh, this is over. Hayashi-san, do you have any comments?
Just a moment. Yes, sorry. So I put on chat the URL of Limo. So if possible, we want to discuss by using Limo after this presentation. So now, indeed, now I'm preparing the found application for the joint collaboration between the SUSTech and Nagoya. This is the final stage. So I hope this one is accepted. So if this one is accepted, I can provide so much money for travel between the two institutes. So thank you very much.
Okay, that's wonderful. Thank you very much.
So please go to the remote. Thank you very much.